The adverse environment of today's battlefield is a more important consideration than ever before. This is a result of the continued evolution of smoke as a countermeasure, the generally high density of aerosols on the battlefield, and advances in weather forecasting ability. With more accurate weather data, the enemy can plan and initiate offensive operations under adverse weather conditions. This capability, coupled with the enemy's propensity to operate in adverse weather, means that the effects of adverse weather may be much greater than its probability of occurrence. Thusly, it is imperative that the Army develop sensor systems for target acquisition and engagement to allow use of tactical weapons in adverse environments. With the incorporation of adverse environment sensors, airborne anti-tank systems such as the Advanced Attack Helicopter can effectively operate under conditions of fog, smoke, dust, and other battlefield aerosols. The Advanced Attack Helicopter is equipped with an integrated weapons system, including TADS, Hellfire modular missile, 30mm chain gun, and 2.75-inch rockets, incorporating a variety of warheads. The program manager for the Advanced Attack Helicopter has determined that an adverse environment capability for the Advanced Attack Helicopter must be evolved. This capability is referred to as HAWTADS, standing for Helicopter Adverse Weather Target Acquisition and Destruction System. The functional requirements to be performed by the Advanced Attack Helicopter Weapons System, complemented with HAWTADS, are: acquire and engage armored vehicles in adverse environments, defend against air defense threats in adverse environments, defend against air threats in adverse environments, aid navigation of Advanced Attack Helicopter in adverse environments. Although a simplification, sensor selection for operations in adverse environments may be viewed as a trade-off between the operating range, as determined by atmospheric transmission, and the angular accuracy, as determined by sensor resolution. The longer wavelengths of microwave sensors, as compared to infrared wavelengths, allow excellent penetration of adverse environments. However, the wavelength size also results in reduced angular resolution and sensor accuracy. Conversely, infrared sensors, because of their short wavelengths, have high resolution and accuracy, but have reduced effective operating ranges. Clearly, the way to maximize tactical advantages in adverse weather is to use millimeter sensors, which simultaneously provide acceptable operating range and accuracy. In recognition of this problem area, a number of millimeter sensor technology programs are now underway in the research and development community within government and industry. The following are representative programs of the efforts underway. MARFS, a 17 gigahertz all-weather radar seeker utilizing advanced signal processing to achieve high clutter rejection and provide for the acquisition and tracking of stationary targets. STARTLE, a 94 gigahertz radar being developed for target acquisition and fire control for tank-to-tank warfare in adverse environments. In this configuration, it is mounted on the M60A3 as a complement to the tank's existing fire control system. Millimeter radar, an experimental brass board of a millimeter tracking radar operating at 94, 140, and 220 gigahertz, with a television camera mounted on a 1 meter diameter dish antenna. AMTT, an all-weather airborne moving target tracker using MTI. Millimeter radar seekers, 35 and 94 gigahertz contrast seekers mounted side by side with a television camera between them. And the WX-50 radar, a pod-mounted 35 gigahertz radar for target acquisition and navigation. Several hardware verification tests have been conducted. To provide a visual record of performance, Some of the tests were conducted with a television camera, bore-sighted or slave to the millimeter sensor. The experimental millimeter radar, operating at 94 gigahertz over rolling, grassy terrain, was used to track ground and air targets out to 3 kilometers. Here, the radar is tracking a tank. The crosshair represents the radar line of sight. Then, an air target was tracked. Then the tank was tracked in hexachloroethane and white phosphorus smoke. The AMTT, Airborne Moving Target Tracker, was evaluated during a series of captive flight tests. First, tracking a ground target in tree clutter. The smaller crosshair represents the instantaneous apparent target location, while the longer, more stable crosshair represents the line of sight after signal processing. Then a ground target in range. And a ground target in dust. Testing of the MARF's all-weather radar seeker occurred under moderate to heavy rainfall while tracking a ground target. Using polarization diversity processing, the target was tracked automatically without interruption through a high clutter area. You have now seen a demonstration of technology illustrating adverse environment capabilities of millimeter wave sensors. In any sensor system, these basic functions are necessary: acquisition, tracking, fire control, guidance, and navigation. Millimeter radar sensor systems, with their combined transmission and accuracy capabilities, can perform these functions and offer ability to perform the HAWTADS functions of acquire and engage armored vehicles in adverse environments, defend against air defense threats in adverse environments, defend against air threats in adverse environments, aid navigation of advanced attack helicopter in adverse environments, thus allowing distinct tactical advantages during operations in adverse environments.